work on proofs because we can prove the correctness of software using tools called interactive theorem provers or proof assistants. Using proof assistants, we specify what we want to have as software and prove that our implementation is correct in terms of our specification. This approach is called complete formal verification, and we already have some success stories of complete formal verification. In Australia, Professor Klein developed a fully verified microkernel using a proof assistant called Isabelle HOL. So, Isabelle HOL is the name of a proof assistant. But theorem proving isn't always about verification of computer systems. Maybe some of you have read this article from Quantum magazine. While discussing the role of computer in mathematics, it introduced the work done by Professor Thomas Hales. Professor Hales used Isabelle to prove the 400-year-old problem called the Kepler conjecture. Isn't it fascinating to advance mathematics using computer? Among many challenges in theorem proving, proofs by induction is perhaps one of the most important and difficult problems. Often, deciding how to apply proofs by induction is the crucial first step when developing non-trivial proofs. For example, this is a proof snippet from the CellFlow project I mentioned earlier. In this snippet, the CellFlow team specified a lemma in line 55 and applied various tools called tactics from line 58 to line 76. In their proof script, the first thing they did is to apply the induction tactic in line 58. And it is important to pass the appropriate arguments to the induction tactic here. And if we apply the induction tactic wrongly in line 58, that single mistake negatively affects the rest of the proof attempt. And don't take my word for it, prominent researchers have been emphasizing the importance of proof by induction for decades. For instance, in this paper published in 1999, Professor Alan Bundy wrote that inductive inference is a vital ingredient of formal methods for synthesizing, verifying, and transforming software and hardware. Because of its importance, many researchers worked on the automation of proof by induction. People tried various approaches including the waterfall model, rappelling, proof planning, and theory exploration. But if you look at how proof engineers work in 2020, you probably find out that they are still trying to figure out how to apply induction for their problems manually. Because this is a difficult problem. In fact, we even have a summary paper describing how difficult proof by induction is. In that paper, Professor Gramlich argued that inductive theorem proving will only be successful for very specialized domains for very restricted classes of conjectures. He even went on to say, "We are convinced that spectacular breakthroughs are unrealistic in view of the enormous problems and the inherent difficulty of inductive theorem proving." So I spent the last 4 years of my life to debunk his bleak conjecture. The first thing I tried is to develop a proof strategy language, PSL. Let me show how PSL works. This is Isabelle HOL and its default editor. We are now looking at a theory file named fmcat. To use our tool, we have to import smart Isabelle using the import keyword. First of all, we have a reverse function for lists. I took this definition from Isabelle's standard library. If we apply this function to a list of 1, 2, and 3, it returns the list of 3, 2, and 1. We have one more definition of a list reversal, itereb. Itereb is defined using tail recursion. I took this definition from Isabelle's tutorial. Now we want to prove the equivalence of two reverse functions. Since both reverse functions are defined recursively, probably we can prove this theorem using proof by induction. To apply induction, Isabelle offers the induct tactic. But to use the induct tactic effectively, we often have to analyze each proof goal and pass arguments to the induct tactic. For example, we have to decide on which subterm we should apply induction, which variable we should generalize before applying induction using the arbitrary field, which induction rule we should pass to the rule field. These are mind-boggling problems, so let's automate this process using proof strategy language. We already have a rough idea about how to attack this proof goal. Namely, we know that we should apply some sort of induction. So, in line 15, we defined a proof strategy called D-ind. D-ind is a sequential combination of three sub-strategies: dynamic induct, auto, and it's solved. If we apply D-ind to our proof goal using the keyword find_proof, PSL's interpreter executes a brute force search based on the search strategy specified as D-ind. For this particular proof goal, we are lucky. PSL's interpreter does find the proof script, which appeared in the output panel. And we can copy this proof script to the right location in the proof document with a single click. So, PSL works well for small, easy inductive problems. But when attacking difficult inductive problems, PSL's interpreter can't find a proof using a brute force search. And when it can't find a proof, it can't produce a recommendation. That's why we developed Smart Induct, so that it can recommend how we should use the induct tactic without completing a proof search. Now, instead of PSL, let's try to apply Smart Induct. We can invoke Smart Induct simply by typing smart_induct in an ongoing proof attempt. Then, Smart Induct analyzes the syntactic structure of the proof goal at hand to show most promising candidates in the output panel. Unfortunately, we can't tell how long it takes for Smart Induct to produce recommendations in advance. And the time necessary for Smart Induct varies for different problems. So sometimes we have to wait for a while. We'll get back to this issue when we talk more about the execution time of Smart Induct. Now Smart Induct produced recommendations. The most promising candidate is proof by induction on XS while generalizing YS. And we can copy this recommendation to the right location in our proof document with a single click. Since Smart Induct does not rely on a proof search, the resulting recommendations are not always correct. Let's see if we can complete the proof of this lemma following the recommendation from Smart Induct. If we apply auto, yes, auto discharged all remaining sub-goals, and we can finish the proof. That's how Smart Induct works from user's perspective. Now let's look at what happened inside Smart Induct. When we invoked Smart Induct, it produced variants of combinations of arguments for the induction tactic. This part is very similar to the first part of dInd. In step 2, Smart Induct applies various induction tactics produced in step 1 to the proof goal at hand, and quickly checks if each candidate is worth further investigation. For example, step 2 checks if a candidate induction returns any results within a predefined timeout. If an induction tactic doesn't return anything, we can't proceed our proof attempt. So Smart Induct discards such combinations of arguments in step 2. In step 3, Smart Induct applies 19 heuristics to evaluate the remaining candidates. Each heuristic is a function that takes a proof goal at hand and the argument passed to the induction tactic. The function returns true if the arguments are compatible with the heuristic, and it returns false if not. For each heuristic, Smart Induct gives certain predefined points to each induction tactic if the heuristic returns true for that candidate. After applying 19 heuristics to all candidates, we reorder the remaining candidates to present the most promising ones in the output panel. I guess you are wondering what kind of heuristics we used to develop Smart Induct. But before explaining the heuristics we used, let me clarify one thing. It is a difficult task to encode induction heuristics that are not specific to particular problem domains. To encode induction heuristics for Smart Induct, we first looked at existing proof scripts and learned how to use induction tactic. Maybe we have this proof script about 2 reverse functions at hand. However, when users invoke Smart Induct, they have their own proof goals. Maybe a user wants to prove something about the execution of an abstract stack machine. This proof goal consists of new constants, new variable names, and new types. In the slide, I used blue to denote what we can see while developing Smart Induct, and I used red to represent what will appear after I release Smart Induct. These constants, names, and proof goals in red come into existence only after we develop Smart Induct. But still, we want Smart Induct to recommend how to apply induction to this new proof goal. This means induction heuristics we encode should be able to analyze problems that do not exist yet. In the beginning, I was encoding such heuristics in Isabelle's implementation language, standard ML, but it was too tricky to encode induction heuristics for proofs goals that do not exist yet in general-purpose programming language like standard ML. So we implemented our own domain-specific language specifically designed to encode induction heuristics. If you are curious about this language, please have a look at our paper on Lifter. In this talk, we only show one example heuristic written in Lifter. This is an example heuristic in Lifter, in which we have implication, conjunction, variables for induction rules, variables for terms, variables for term occurrences, and variables for natural numbers. We also have universal quantifier and existential quantifier. Let's see how this example heuristic processes this proof by induction. In this proof, we applied what's called functional induction by specifying induction variables xs and ys and an induction rule itRev.induct. This heuristic first checks if there exists an induction rule passed to the induction tactic. Yes, in the model proof, we used itRev.induct as an induction rule. Then, we check if there exists a term T1 and its occurrence T01 that satisfy the following conjunction. Now let's focus on this term itRev and its occurrence inside the proof goal. Then we can say that rule 1 is a rule about term occurrence 1 because rule 1 is itRev.induct and term occurrence 1 is itRev. Now in the second part of the conjunction, the first construct is the universal quantifier over induction terms. In this proof, we have two induction terms, xs and ys. So term 2 is xs and ys. The second construct is an existential quantifier for term occurrences of T2. And let's focus on their occurrences on the left-hand side of the equation. For the last existential quantifier, we check for all induction terms. There exists a natural number n, such that the induction term is the nth argument of itRev and the nth argument of the induction tactic. When T2 is xs, this is true because if we fix n to be 1, we can say that xs is the first argument of itRev in the proof goal and it is also the first argument of the induction tactic. This is also true when T2 is ys, because ys is the second argument of itRev in the proof goal and the second argument of the induction tactic. So the existential quantifier holds for all induction terms, and we can evaluate the second part of the large conjunction to true. Since we evaluate both conjuncts to true, the entire heuristic returns true, which means our heuristic correctly judged that this good application of induction is indeed good. In other words, the heuristic succeeded. What happens if we apply the induction tactic in a bad way to this proof goal? Here we have the same lifter heuristic and same proof goal, but the application of induction is bad. We flipped the order of induction terms. If we apply the lifter heuristic to this application of induction tactic, there does not exist a natural number n that satisfies the conjunction. So the lifter heuristic returns false to this bad application of induction tactic, which means the heuristic correctly judged that this application of induction is bad. In other words, the heuristic managed to differentiate good applications of induction tactic from bad ones. So that was one example heuristic out of 19. The remaining obvious question about smart induct is its performance. Does it really work? You would ask. To answer that question, we evaluated smart induct using 5 theory files with 109 proofs by induction from the archive of formal proofs. For these 109 proofs by induction, we counted how often the recommendations of Smart Induct coincide with the choices of human engineers. This is the result. The blue bars are labeled as top 1. This means the blue bars indicate how often Smart Induct recommends the choices of human engineers as the most promising induction tactic. On the other hand, the green bars are labeled as top 10. So green bars indicate how often the choices of human engineers appear among the top 10 most promising candidates recommended by Smart Induct. Challenge, DFS, Goldstein, NN, PST are abbreviations for theory names, and you can find the overall results at the right end. I guess the first thing you noticed in this figure is the poor performance for NN, which stands for nearest neighbor. So it is natural to imagine that the performance of Smart Induct heavily depends on problem domains. But if you look at these theory files closely, you might notice that the performance gap might come from the different styles of induction. In this figure at the lower left, we counted how often proofs by induction have any arguments in the rule field of the induction tactic, and how often proofs by induction involve variable generalization. As you probably noticed, most proofs by induction in NN involve variable generalization, and I think this caused Smart Induct's poor performance for this theory file. In fact, when we counted consciousness rates for NN, again ignoring variable generalization, the performance of Smart Induct is not that bad. Now we rearranged consciousness rates for the same evaluation set based on the use of the rule field and variable generalization. W here stands for with, and WO stands for without. For example, the leftmost group reads W rule W arb. This means the induction tactic has an argument in the rule field and the arbitrary field, which we use for variable generalization. Again, we can confirm that Smart Induct performed poorly for those problems that require variable generalization. So I have to admit that I didn't solve the problem of generalization heuristics. Now we know that we have an unsolved problem about proofs by induction. Am I doing something about this? Sure. We have a new version of Smart Induct which is developed in a new domain-specific language. I will release this new version soon, so stay tuned. Before finishing this video, I should explain the execution time of Smart Induct. As I mentioned earlier, the execution time of Smart Induct varies depending on proof calls. This figure ordered each invocation of proof by induction in the evaluation set based on the execution time. Note that we are using the logarithmic scale for the vertical axis, which means Smart Induct works pretty fast for some proof calls, but it can be very slow as well. That's all from my side, and thanks for watching this video. If you enjoyed, please visit our GitHub repository or read our paper. See you.